In this problem, we've got an electron that is passing through an accelerating region. So it's entering that region with one speed, and as it's in that region, it's being sped up to another speed. We're told that the acceleration is constant, and we're being asked to find that acceleration given the length of the region and the initial and final speeds. Now, the acceleration being given to us as constant is a very important detail because it means we can use any of our kinematics equations that apply to situations with constant acceleration. So I've written out the three main kinematics equations on the side over here. Now, when we have a problem like this, the idea is that we want to choose the equation that contains the variable we're trying to find and has no other unknowns. That is the ideal case we can look for in this kind of problem. So let's make a note of the variable we're trying to find and the variables we have. So for the variables we're given in this problem, we're told that the length of the region L is 1 centimeter. So that's a 1 centimeter distance of the acceleration, which in the context of our kinematics equations can be seen as the delta x. So that's given to us in the problem as 1 centimeter, and generally we're going to want to convert that into meters. So remember, there are 100 centimeters in 1 meter. So to convert this into 1 meter, we just divide the centimeters by 100 or move the decimal point 2 spots to the left. So this means that we've got 0.01 meter, though technically those last two zeros are also significant. But for the purpose of the math, we could just put in 0.01 meters. The initial speed is given to us, v naught, as 1.50 times 10 to the power of 5 meters per second, and the final speed v is given to us as 5.70 times 10 to the power of 6 meters per second. And the variable we're trying to find is the acceleration, or a. That's the question mark, the thing we're trying to find. So again, of the three equations that we typically use for constant acceleration, we want to figure out which equation is best going to be used because it has the acceleration, which is all three of them, so that doesn't help much, and which equation has all of our knowns, and no other unknowns other than the thing we're trying to find. And just from looking at this, we can see the first two equations aren't going to help us much because they both have time, which was not given to us in the problem, so we can just ignore that. Same thing with the second equation because there's the time squared. The third equation we will be able to use because it has acceleration, which is what we're trying to find, and it's got v, v naught, and delta x, which are all things we know. So the only unknown in that equation is the acceleration, which means we can take that equation, solve it for acceleration, and get our answer. So that is what we will use. So we're going to be using the equation v squared equals v naught squared plus 2a delta x. Because acceleration is what we're looking for, we're going to need to algebraically rewrite this equation to solve it for a. So we're first going to subtract v naught squared from both sides of the equation. So we'll end up with v squared minus v naught squared equals 2a delta x. And then we'll divide both sides of the equation by 2 and delta x. So this gives us an equation of acceleration equals v squared minus v naught squared, all divided by 2 multiplied by the change in horizontal position. So all that's left for us to do at this point is plug in the knowns into the variables of those equations and get our final answer. So a is equal to the square of v, so that's the square of our final speed, which was given as 5.70 times 10 to the power of 6 meters per second. And don't forget to square that entire value because our v is squared. Then we subtract the square of the initial speed, so that's 1.5 times 10 to the power of 5 meters per second. Square that whole term as well. And then divide all of it by 2 multiplied by, in meters, to keep the units consistent, the length of the region, the delta x, the change in x, which is 0.01 meters. And no squaring has to be done in that denominator. If we put all this into a calculator, we get a fairly large number. A calculator will most likely put this into scientific notation automatically, which will give us an answer of 1.62 times 10 to the power of 15 meters per second squared. And that is the acceleration that we're looking for. So this is the acceleration that's caused the electron to accelerate from 1.5 times 10 to the 5 meters per second to 5.7 times 10 to the power of 6 meters per second over the course of 1 centimeter. And that is it for this problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out making more videos like this. If you have a request or a question, leave a comment down below, and I hope you all have a lovely day. Bye-bye!